Okay, so now we've learned about the transformation, the rotational matrix. We've learned about translation, where we can just add a vector to our existing vector. Let's go ahead and see how this works within just a single link. So, we're going to go ahead and we're going to draw our link relative to the local plane, because within a local plane, our link is not going to change. We can say that the distance from B to C won't change, the distance from B to P won't change. In this case, we're going to refer to B to P as SP prime, because that's in our local X prime, Y prime coordinates. And the reason we know that all of these things are constant is because all of the details that we're dealing with in this class are dealing with rigid bodies. If it's a rigid body, by definition, the coordinates between points on the body are constant. So when you're dealing with something like a spring where that's not the case, you'll have to change up the rules. But for now, this is what we're dealing with. And we can say that in the global plane, we have the distance r, which goes from R to B. And if the distance r goes from R to B, then we also have SP, which is the distance from B to P in XY coordinates. So the vector itself doesn't matter which coordinate systems you're using, because a vector is a magnitude and a direction. The coordinates are how we express the vector. But SP is when we express it in the XY plane. And if we wanted to discuss point P, we could say that RP, the distance from the origin to P, would be equal to the vector R plus the vector SP. So that'll be our vector RP. And you could see that on my graph, I don't have the hats that say it's vectors, because we have that those are also our magnitudes when written without the hat, and the vector, the direction part, is drawn. But when we're writing as equation, we refer to it as R hat and SP hat, RP hat. So if we add up those two vectors, it gets us to our endpoint. So let's switch that around, and we're going to say that our endpoint is equal to R, which represents the translation of the link, because that's how much one point has translated. And then we're going to have our rotational matrix that's all based off of how our system has rotated with respect to everything else. So here we had that X prime was in this direction. If we draw a line vertical, we would see that phi is going to be based off of the distance between the horizontal and X prime. So that would be R cosine phi minus sine phi, cosine phi matrix. Oops, that's a theta. Let's fix that. And that allows us to apply a rotational matrix. So now let's look at just a standard example link. And we're just going to have it be a straight bar link that has one length. Here we have it in our local coordinates, and we could say R prime is the coordinates where it has length R. There's no angle, because when we talk about local coordinates, we're talking with respect to where we are. Now, if we then tilt our link up, because it's rotated a bit with respect to theta, we can say that R is equal to our A matrix times R prime. And that's going to be that cosine theta minus sine theta cosine theta times R0. And so now we're using theta and not phi, because phi was how we defined it. In this case, we have a specific theta. And we also see that this matches the definition that we had for a link at the very start of this unit when we started this last week, or, if you're watching videos, whenever you watch the video. So this will now give us the tools to talk about a linkage system as well, because we will have multiple thetas, we'll have multiple link linkages. If we wanted to add on a detail, we could also say this is equal to R times cosine theta, sine theta, and the other thing that we learned was we can refer to that as R times E, where E is our unit vector for the link. And that's what changes with a linkage. For most linkages, the radius doesn't change, but we're going to see an example of one that it does change. So let's go forward. So we're going to do a position analysis of a 3-bar linkage. And you might be thinking to yourself, well, in class you explained that a 3-bar linkage was a structure. And that's true. I showed you a 3-bar linkage that was a structure. In this case, we're going to switch something up a little bit. So we're going to have our ground is still defined by D. We have that our crank is A. And then we're going to have a device called the slider. And so we could describe this linkage as having a crank, a slider, and a ground. So it's no longer the coupler and rocker because we only have a 3-bar linkage. We have a slider. And that slider is connected with a half joint. So how many degrees of freedom does this system have? Well, there's a little question. Here's a good place to press pause if you want to play along at home. And we can see that there's 3 linkages. So we'll start 1 for ground, 2 for the crank, 3 for the slider. Pin joints, we have 1 between the ground and the slider, 1 between the ground and the crank, 1 between the crank and the slider, and then between the ground and the slider, we have a half slider, because the link can both rotate and translate along one axis, which means that it has only lost 1 degree of freedom as opposed to the standard 2 degrees of freedom that you lose with a pin joint or a full slider. And that means that our degrees of freedom should add up to 1, and we see that they do. So because our degrees of freedom add up to 1, that means that we only need 1 piece of information to tell us everything we need to know about the slider. And we're going to say that piece of information is the angle between the crank and the ground. And if we know that, then we will be able to know everything about this linkage. So let's go ahead and do that analysis. So we have a vector loop, and we can say that we have our angle theta 2 is connected to R2 for our crank. That's relative to the horizontal for theta 2. We have theta 3 is relative to the horizontal, and we have R3 connected there. And then we have R1 that goes from the horizontal, from the origin to the point at which the ground connects to the slider. And if we do our vector loops add to 0 because we end up where we started. So we can say R2 plus R3 minus R1 is equal to 0. And I'm getting close to that 10-minute cutoff. This will be a longer video, but at least there is a video. So we have R2 is A cosine theta 2, sine theta 2 is equal to A E2, where we have those unit vectors E2, E3. We also could have a unit vector for, pause. Okay, because I had something I wanted to say here. So you might look at R3, and we see that it's equal to B times cosine theta 3 and sine theta 3. And so that tells us that we will have B times cosine theta 3 will be our x-coordinate, B times sine theta 3 will be our y-coordinate. But when we look at R3, we can see that there is clearly a negative y component, but I don't show that in this matrix. And the reason for that is we are measuring relative to the horizontal. If you measure below the horizontal, that gives you a negative number for theta 3. And with a negative theta 3, we would end up with a negative sine theta 3. So we have theta 3 is a negative number, and so that means that cosine theta 3 would stay positive, sine theta 3 would turn negative. And just in case you had that as a cut-up, we can point that out. Then we have R1 is just D10 because the unit vector is only along the x-axis for the ground. And if we wanted to add an extra vector, we could have the vector RBP is equal to the length P times our unit vector E3 because it's going the same direction as our R3. So we have those four vectors. We're only going to focus on those first 3 for now. because those are the three that are represented in our vector loop. So we can't go all the way to RBP because that would put us off the loop. If we added that, you would see you wouldn't quite get to the origin. But let's add up our vector loop, and then we can do the algebra to get us to solving this problem. And I'm just going to keep going and have this be a longer video. I know I said I wanted to keep them under 10 minutes, but we're on a roll. So we have our input is theta 2. We talked about that on the last slide. And then looking at this matrix equation, we can see that we have A is known because that's the length of the crank. B is unknown because that can change. So depending on where theta 2 is, the length of B2 from the start of the slider to where it meets the ground changes. So B is an unknown. Theta 3, that angle for B, is also unknown, but then D is a known value. So that gives us two variables that happens as a result of our input theta 2. And that means that we have two equations, two unknowns, and it should be a solvable equation, a solvable system to find. So let's go ahead and solve this system. So A cosine theta 2, A sine theta 2, same equation that we had before. We're going to take this one at a time and solve it manually. And I'm going to tell you that MATLAB can do it faster, but let's go through it ourselves. So we can say A cosine theta 2 plus B cosine theta 3 minus D is equal to 0. Now let's go ahead and manipulate this equation so that we are solving for B in terms of our other constants and variable. So we have B cosine theta 3 is equal to D minus A cosine theta 2. And then we could divide by cosine theta 3 to say B is equal to D minus A cosine theta 2 divided by cosine theta 3. Take our second equation and say A sine theta 2 plus B sine theta 3 minus 0 is equal to 0. But instead of writing B, we're going to go ahead and plug B in from the way that we found it above. And we can manipulate this equation. And to save ourselves some hassle, we'll remind ourselves that sine over cosine of a given theta is equal to tangent. So we could say tangent theta 3 instead of sine theta 3 over cosine theta 3. And that way we could solve everything in terms of the tangent. So the tangent, we can go write that ahead. And then the tangent would be equal to minus A sine theta 2 over D minus A cosine theta 2, which looks a little sloppy. I don't like having too many negative signs in my equations. So let's go ahead and multiply the top and bottom by negative 1. And that would give us A sine theta 2 over A cosine theta 2 minus D is tangent theta 3. So now we have theta 3 in terms of our known quantities, and we have B in terms of our known quantities and theta 3, which we just proved we could find out. This is a solvable equation. So that's good. But we were interested in where point P was, and we did not find that yet. So we've got a little bit more algebra to do. So if we want to find the radius to point P as it moves around, because that's the point at which exciting things are happening, what we do is remind ourselves that we have R2 and RBP. And we could say that RP is equal to R2 plus RBP. And R2 is just A times the unit vector E2, which is in terms of cosine theta 2, which we have. And then instead of RBP, we could say that's equal to the constant P times E3, where E3 is in terms of cosine theta 3, sine theta 3. So those are quantities that we're able to find out. Because we're able to find them out, we can find RP. So all of this is doable. We can handle it. But when we want to find our analysis for every position, we don't want to go ahead and manually calculate everything in for every point on this link. So we're going to find out that MATLAB is a much easier way to go through this. And we will do that right now. Or, during class time and, this video is over. I'll talk to you later. So, doable but tedious. Let's go to MATLAB.